Hey, morning everyone. My work is mostly on XPS that relates to batteries. So because I'm funding a Canadian student action, I have to put on this on my front page. But so I'm in working with Rob at UCL, and I'm trying to understand the electrochemical processes happening at the electrode light interfaces using operand XPS.
Okay, so I can fix it.
Yeah. So surface characterization is very important for people who are working in factories and catalysts as well. And we can do it in different ways. At the lab scale, we can use the photoneal electron processes, XPS standard. And we can move on to synchrotrons, where we can use the photoneal and photonow processes to look into the surfaces in a different way, where both these processes correlate with each other. But the main issue that we need to address is UHV. So we need to have materials, either we need to engineer materials that are stable in UHV, or we need to use materials that can be used straight away in UHV. And for electrochemical processes, electrolyte is one of the important bits. Standard electrolytes are very much not stable in UHV. So you need to work around that and find new electrolytes that are stable, or use solid state electrolytes. But I'm proposing, or I'm using ionic liquid in this case. So okay, so I'm using ionic liquids in this case, and advantage of ionic liquid is like if you can design it properly, they can be liquid in the room temperature, and they are stable in heavy conditions because of the low vapor pressure. And the other practice stuff, another strategy stuff that you can do is like they have quite good solvations as well, so you can use them. And because they are stable in USB, so you can incorporate them in the XPS to perform some standard electrochemical processes in situ. You can see that I have placed ionic liquid in USB in 10⁻⁹ bars. It was there for like 1 week at least, and it was kind of stable, and the spectra were on side identical. So they were very stable. So only change in spectra could be due to the degassing of the sample. And liquids tend to absorb gases and water pretty easily, and it slowly tends to degas, and then that might lead to the change in the spectral features. Okay, so before we move on to how we investigate ionic liquids, it's very important to how we look into the spectra of ionic liquids. And I look into different combinations. What we do in standard XPS is that either you charge concentration using flutons, you do some filtration with argon guns and different Excel sources. And I did all the combinations of it and then modeled it. And I found that the best condition to do or to look into the spectra of ionic liquid is to first etch the surface with I would say 100 to 200 degrees of soft surface etching, and then do the XPS analysis on this. So you remove all the adsorbed gases and the water molecules on the surface, and then you look into the then you get the proper spectra of the ionic liquid in it. So this was a very important thing that I would suggest. Yeah. Okay, so in terms of biasing, so I use a standard bias. So what you do in measuring the UPS spectra, so you can bias the ionic liquid. So this is the helium-2 spectra of the valence band of ionic liquid, and this is just like -1 to +1 volts. So I have biased it till -9 to +9 volts as well. So at that potential as well, so this is quite stable. So there is no change in the valence band spectra. So I would say there is no change in chemistry of the ionic liquid, so they are quite stable in USB and under high biases as well. But to measure the electrochemical processes, so we need to consider how we look into the surface as well. So because of the angles at which the X-rays come and how the electrons are being collected, we need to have a proper alignment of the electrode as well, and to look at the interface as well. So we need to match the interface with the angles of it as well. So it was kind of difficult and it was quite challenging at the initial stages, and how to load the sample and how to load the electrodes and everything. It took me quite some time. But the other thing is like the material that you use to store dynamic liquids, the same that you use to store dynamic liquids, needs to be stable, because what happens like I actually prepared the cell in different materials. But what happens like when I put it in it's kind of stable in the outside atmosphere, but then when I put it inside the XPS, it can leak because of the pore structure. And that's a quite important thing. So the cell should be leak proof to the dynamic liquid. So before you even real chemistry inside, first test it if it is leaking or not. Then we came up with this design of different cells that kind of matches the angles of 55 degrees or almost 55 degrees. And then you can see the interface. This is a dummy copper electrode that we are used. So I can see both the electrode and electrolyte at the same point, So I can see the interface, I can say that I'm seeing the copper and dynamic liquid as well. So this is where kind of the design we can opt out for future measurements in doing electrochemistry in field. Okay, so then we went to thermo. They have to do the measurement, we need to have the biases applied from outside, and so thermo gave us the instrument to use in XRG2. So they have the stage which can be connected to external bias. So it is a standard 3-electrode cell. So all 3 of them are platinum in here, and I can apply bias and see how it is cycling inside the XPS in UHV. So I cycle it between 2 different potential windows. I can see the oxidation and reduction of the liquid as well. You can see at the different biases, you can see the changes in the spectrum of the liquid as well. So yeah, this is the first point where we started looking into the electrochemical processes inside HPS using liquid media. And hopefully we can use this for any other chemical processes, electrochemical processes, where you can have a stable and a finite liquid with a larger potential window, and you can do the electrochemistry within that potential window and look into what happens to the catalyst or some of the material operand are using XPS and electrochemistry together. So this is one example that I did with this setup. So I mixed some vanadium salt, vanadium acetonate in the liquid media, and I can see that there is no. I hope to see some changes in the vanadium peak position or vanadium charge state, but it didn't happen. So what I saw is that the entire of the vanadium salt was moving between the electrodes when I applied the bias. So I looked into the working electrode. At a positive bias, I can see the vanadium peak there, but when I reverse the bias, entire of the vanadium salt moved to the other. So there is some charge migration happening with that bias. So that was quite interesting to see in situ as well. Okay, so this is the next stage where I move to a next stage, look into proper electrochemical processes. This is more related to battery, but we can use it for the applications as well. So here it's ionic liquid mixed with some sodium salt. We are looking into the sodium changes in the sodium spectra or sodium signature with charging with applied bias. And here we have a standard aluminum foil. I made it as L shape to get a proper view of the interface. And there are 2 kinds of platinum electrodes which are acting as a counter and reference electrode as well. And it was very important to look and find the interface first. So we have to do a line scan. So take a large area and do the spectrum at each point to see where we are seeing both the aluminum and ionic liquid together. So we moved from the one point where we are seeing just ionic liquid and moved till a higher point where we are seeing just the aluminum, so no ionic liquid there. So we have to choose a point in between where we can see both the carbon signal and the aluminum signal together. Okay, so these are the 2 points that I chose. For what we started when we looked into the cycling inside, what we saw that with the flood gun on, so the standard process we by default the flood gun sits on. And what happens is that we couldn't see anything happening to the sodium salt and the ionic liquid as well, because whatever bias or the charge we are giving from outside is compensated with flood gun. And for that reason, we stopped the flood gun and then started looking into the electrochemical processes, and then we found some interesting bits happening in here. And the important bit is like you need to always have two reference points. If we take the ionic liquid, if we see any change happening, we don't know if it's happening due to the external bias, because if you see any standard HPS spectra, it tends to shift with applied bias and everything else. So we need to differentiate between the electrochemical processes and due to the standard applied bias in it from the in the electrochemistry happening. To differentiate that, so we took two reference points. The point one is the interface, and point two is just a drop of ionic liquid on the aluminum foil on the aluminum electrode, which is kind of separate from the electrochemical processes. Okay, but the next important bit, like how fast we take the spectra. So the electrochemical processes are like we cannot make it too slow, we cannot make it too fast. So we need to optimize the electrochemistry and optimize that with how fast we take the spectra, because and it's restricted to the instrument as well. So what we use, we use the sampler process, which the XPS in sampler process is like you and the instrument take an entire of the express entire of the electrons, and it just plots it. So what will happen is that we take a fast spectra, but it is loses its I would say resolution. So if you see the red one, the orange one, it is taken at a snapshot, high fast spectra. But we see that we see there is some features are there, but it is not exactly what we can fit into. So we need to always have a reference spectra to match time there. So the green one is taken with a longer exposure, so the slow standard XPS spectra, and that's what the drawback. So if you want to optimize electrochemistry with the XPS, we tend to lose some information on the spectra, but still we get something out of it. So this is what's happening in the standard snapper process in when I did the XPS inside. So we run the DDX standard side cycling inside. And what happens is that you can see the snap map, which the intensity of the carbon is correspond to the C1S carbon B. And then with the applied bias and the maximum bias, you can see there is change in the fluorine and aluminum as well. So, and from the CV cycling, we can convert it to the time and then correlate the time with the XPS time peak, and then match that to each other. And so that, okay, at this point of time, we are seeing this chemistry happening in the electrolyte space. And this is the most important bit. So I told you about point one and point two, and the point one, which is just stop on the electrode and liquid with some sodium salt in it. So what is happening is in the point two is due to the charging of the surface. So the aluminum has been biased from external source. So whatever is happening is the bias. But if you see the point one, which is just at the interface, the fluorine peak is very different. So in point two, which is the interface, we are seeing the chemistry happening with the external bias during the cycling. So it's very important to have a reference in situ when doing the measurement as well. And then we moved on to different bias, different cycling, different potentials, and up to 2 volt we didn't see a change in chemistry of the sodium strength and sodium ascent. But when we move beyond the -2 volts at -2.2, we see the formation of sodium chloride, which is what we tend to see in ACI when battery is cycling. So this is an important bit. So we know at this potential we start to form sodium chloride, which is the main part of ACI. And also did some chrono measurements as well. So at point one, I didn't see any change in sodium, which is from the ionic liquid. And at the point one, which is at interface, I can see the sodium changing its chemistry. So there are different peaks coming out with sodium. So there is formation of ACI and the electrode, and there is some interface forming and the electrode. And the aluminum is also unchanged. So whatever is happening because of the sodium salt in the electrolyte. So we can replace this sodium with some other catalytic materials and then measure how the catalysis is happening in situ using ion liquid media in a standard electrode cell. Okay, this is one of the reference paper that we found that they use the ionic liquid and just put palladium salt in it, and with time the palladium changed in oxidation state. It was just with time, so they haven't applied any bias. The palladium was reacting with ionic liquid and it changed the oxidation state. So we can measure, they measured it, how it reacted, and they did it in an XPS. So this is one of the initial start, and then we can use our configuration in a three state, and then do like more relevant catalytic studies as well. And I'd like to thank Avishek and Friday and Xena for supporting this project and Rob is yours. Thank you.
Are there any questions? Santosh again?
Thanks for this interesting talk, especially with the cell. What are the dimensions of this cell?
So the diameter, so we need to work out the thickness because of the height restriction. So it was around 4 mils the height, but the dimension in terms of dimension, you can increase it to much higher diameters as well. So you can go to at least 2 centimeter in diameter, but the height should be less than 5 millimeters because of the instrument restrictions. But if you have more space between the hexagon and the stage.
But I think it's very good. Already there is quite good enough room for developing cell.
Yeah.
The other one is what's the thickness or volume of the sodium electrolyte? Does it matter? Because
Kind of, yes. If you have too much volume, then we are. So what I use is like it was around 50 microliters of ionic liquid in it with sodium salt. But if you use too much of ionic liquid in it, then the signal is dominated by the ionic liquid, and we lose signal from the interface. So we need to we don't need to have very little, we need to have too much. So that's it. Like
so you need to optimize the volume. Yeah. The other one is that lost.
Yeah.
Is it closed cell or is it? Is it possible to close it? Do we need any windows?
Yes, I don't think we can close it maybe. So yeah.
Okay.
Vice Abhishek. So regarding the vanadium movement, so you said that in vanadium you don't see also an oxidation rate, but then you say complete loss of vanadium over there. So how does it happen? I mean, like on the working electrode.
I don't know. I'm expecting to see the oxidation reduction of vanadium. That's what I wanted to have a potential reference potential.
Yeah.
But it didn't happen. So what happens is that when I applied a positive bias, the vanadium moved towards it.
Yeah.
But when I applied a negative bias, then that I didn't change vanadium.
So
when I reversed the bias again, and again vanadium moved towards it. So without any change in spectral features. So I don't know. It's like vanadium because it's ionic liquid, everything is ionic form.
Yeah.
And the vanadium is just shuttling between the electrodes like we've seen that treatment.
So if it's not under the UHP conditions, if it's at outside and room temperature, do you see the same behavior as well?
I did see the oxidation reduction of vanadium when I did it outside.
Yeah.
It may be due to the presence of water in the liquid because we are in UHP, so there is no water or anything, so no dissolved gases as well. That's why. Another thing is like I didn't push the potential far enough to see any oxidation or reduction of vanadium maybe in that case. That could be one possible.
Thank you.
I think we'll take one last question and then some.
So I was wondering, like, why did not you hold it, different potential instead of scanning? You scan the CV while measuring, right? So instead of identifying the potentials and maybe hold that at potential, because usually when you scan, so it's a problem, right? You see the broad peaks, and then I'm just wondering why didn't you?
I did the chrono as well to see which I found what I found that at that potential I saw that how the sodium is behaving and changing with time. So I can see that as well. But that's the next thing. So I want to increase the potential, go to a particular potential, hold it there, see how the chemistry is changing, and then do time. Because when I put it inside, it takes almost an entire day to pump it down. And I didn't have much of instrument time to do that experiment. But the experiment was, I would say, like for a couple of hours, but setting it up was for the entire day.
Well, last question, is it the electrolyte is in liquid state or solid?
Yes, it is,
It's
yeah.
liquid. And then is it a flow cell or static?
It's a static. I know you guys are making a close.
Right, yeah, that's what I was wondering. Thank you.
Okay, I hope you'll join me in thanking all this morning's speakers.